So there's a competition called AI Birds, which started in 2012, and the goal is to develop agents which ultimately play Angry Birds better than humans do. So far, it's been 7 years, and it's not really been successful. So we've had almost 50 agents, including the baselines, and they use a whole range of different techniques, like heuristics, reasoning, and a bunch more, right? And we're still very far from beating humans. So to illustrate that, here is 21 levels of the AI Birds benchmarks. The humans are in blue, and the agents are in red. And you can see the humans are still quite a bit better. And these are the benchmark levels. These are the levels which the agents have the most access to and can train the most on. So, not just on the benchmark levels. Every year, there's the man versus machine challenge, where we put the 4 best agents against humans, which come to play at H-Night, which was just last week. So we take 4 levels, never seen before, and just let the humans play and the agents play. And there's zero competition, basically. Humans completely destroy the agents every single year. So these agents so far have used a whole bunch of different strategies. Right? These which are fairly typical algorithmic approaches to building agents for games. But humans, we don't really play that way, do we? When we see a level, we look at it, we think about it for a bit. We don't really sorry, technical issues. So we don't really consider what we the strategy we're employing. We just make a shot and we try again, or we try some different strategies. And one thing we observe when playing Angry Birds is that humans restart a lot. So no agent so far has restarted, unless they've absolutely had to, as in failed a level or won the level. And agents, we restart for a whole variety of reasons. And the developers have put the restart button in a fairly prominent position to hit accidentally. So this leads us to the conclusion, right? Absolutely free of any fallacies, that we should restart too. The agents should restart too, because humans perform better. So let me just reach up to my restart oracle, ask it when I should restart, and just get free performance. If only it were that easy, right? So we can think of some situations where we want to restart. Maybe we want to explore the problem, we want to give up when we don't think the level is possible anymore, or we just want to try more shots, perfect the shot that we want to make in our minds. So in problem exploration, we've seen that the best agents so far in the AI Birds competition use different strategies, and they try different ones, whether based on the levels and based on whether they failed or not. So the non-deterministic agents, they sort of fail a level, do a bit of internal calibration, and maybe try another one. And we've seen they've done better than those deterministic agents, which relatively try the same strategy over and over again. We can also, so moving on to giving up on levels, it's a bit difficult to tell when a level is not possible, right? When do we want to give up? I mean, this is the very start of a level. We probably don't want to give up, but it's quite hard to tell if it's solvable or not, right? There's 7 birds, and we have to think very far in advance to see if we can destroy this fairly complex structure. Now, if we reduce this problem, I would probably give up. It's a lot easier to think about when there's only 1 or 2 steps in advance to consider. So we're going to build a model of the world to determine whether the level is solvable. We can use basically any technique we want, like simulations, qualitative physics, reasoning about levels. We can build a machine learning model if we want. But just in this work, we're going to build a preliminary qualitative physics model. So we have relations between objects using the extended rectangle algebra, and we formalize the way to propagate forces between objects. These are fairly common sense, so if you have an object that topples over, the object which it pushes against is probably going to experience another force. And we have a definition, but basically, if a force can reach all the birds, all the pigs, then we just say the level is solvable, right? And this is guaranteed to improve performance. Because if the level is not solvable, there's no point playing the level any further. So, right? If our model is accurate. And then lastly, we can talk about suboptimal shots, right? So in a human, humans are good at judging rough trajectories, but we're not perfect at this. So sometimes we're just a little bit off when shooting on a level. We, try that again. Or when we've made a bad shot, like the bird basically bounces off nothing and hits nothing, then we've not increased the score very much. So we probably want to try again, right? I don't know if any of you play Angry Birds. So if you hit like a wood block with a blue bird, it basically does nothing. You get like 70 points and the block doesn't get destroyed or anything happens. So we've got these rules, right? But is this generalizable? Do we want to always restart when we hit a wood block with a blue bird? And that's a pretty difficult question to answer, right? We're trying to play novel and unseen before levels. So we probably don't want to make such immediate assumptions. So probably want to make a sliding scale of when we want to restart and not make it binary, right? So overall, we can determine when we want to restart based on some combination of rules. Doesn't really matter which combination, we just want to explore and see what happens. And we could tune these weights with using machine learning methods or just use some fixed weights. In this paper, we just use fixed weights to explore what can happen. And basically, we take two level states, before a shot is made and after a shot is made, in order to determine whether we want to restart the level or not. So in the AI Birds framework, the action robot is an interface between the agent and the game, which takes all the commands and lets the agent interface with the environment. So what we're basically doing is treating the agent as a black box. It feeds the screenshots in, and we restart it when our rules determine so. But this also has problems, right? The agent shares no knowledge with our restart module, so we could actually ruin some strategies if we restart without telling the agent. But telling the agent requires quite a bit more investment into developing this module to work internally with the agent's internal rules. So in order to test our restart module, it's a bit difficult. Because there's no ground truth. Like, when should we restart the level? Like, humans can't 100% accurately predict this either, right? So we don't want to manually apply labels. And simulating every single possible shot is quite intensive. And our solvability module isn't fully complete. There's a lot of possible outcomes that can happen in Angry Birds, so we haven't fully coded them all. So what we're going to do instead of having ground truth is attempt the level with the agent, log if we want to restart, and say that's a false positive. The agent successfully solved the level, but we told it to restart. Very simple, right? And this will vary based on the different agents. Some agents are stronger than others in solving certain levels, and some aren't so good. So here we have a naive agent, a random agent, if you will, and we see there's a 20% false positive rate. That's really bad, isn't it? But if we take a look at the actual times it takes, we see that on average it improves 12%. So what does that actually tell us? On this very specific level set, with 21 levels, using the naive agent, we get about 12% better performance, or 12% faster to solve the levels. And again, performance is relative, right? We have to determine whether we want to measure the scores we achieve or how long it takes to solve the level. And if we move on to more complex agents, we just get wacky numbers of these confusion matrices. And we see that Eagle's Wings is actually one of the stronger agents, and it's got a much higher false positive rate than naive agent and the Seabird's agent. And what does that even tell us? So Eagle's Wings can solve more levels in general when we've told it to restart. So that means our module might not be fully accurate. In fact, it isn't in most of these situations. But moving on, we have some further tests. So this is the data lab agent on the 2015 Guerrero-Romero levels with our weighted module and the rules. And we see there's actually a whopping 5% improvement. And this is significant. But the thing we have to keep in mind, though, is 5% is not bad. So within the past 4 or 5 years, the agents submitted to the AI Birds competition haven't actually improved that much. They've sort of plateaued at the at some performance benchmark, which is around 1 million of the benchmark levels. And there's still quite a big gap to close. So any amount of improvement is a step forward. Not to mention, this is with very simple untrained weights, a very simple module of the world which we developed, and there's a lot more we can improve upon. And of course, this is just on one level set. Right. So we can see another level set where it actually got much, much worse. The thing about this is that the data lab agent is actually a bit more deterministic than most. So on these levels, it's decided to use a single strategy. And we told it to restart, and it uses the same strategy again. And it just keeps going, resulting in this level just not being able to be solved. We can fix that. So we can fix the weights, we can change the weights, we can falsify the outputs, right? So in this situation, these two levels would be able to solve if we didn't always restart. Say we have a 25% chance of restarting and we want to restart. So we can also actually take into account the level characteristics when deciding when to restart. And we can do a lot more in general to fine-tune the models that we're using and the rules we're using. So some things we've learned. So when to restart is highly agent-dependent. It will probably be a much better idea instead of treating both the agent and our module as a black box. Probably take that into account when developing new agents. And as we mentioned, in the past 4 or 5 years, the agents have not been really improving in the Angry Birds competition. Really should be doing something different, right? Taking restarts into account, taking everything that we can when developing agents for Angry Birds. Let's get to it.
Hello. Sorry if you mentioned this during the talk and I didn't quite get it, but do you apply the, I'm going to call it the restart system, do you apply it on fixed agents or do you apply it when the agents are being trained for the agents that actually do train?
So we're not actually training any agents. So we're just taking the agents which have been submitted to the competition, basically treating them as black boxes, and we're testing to see how our restart module does with each agent. So
okay, because if that's the case, then I'm not really surprised that some agents may just try and do something and then you restart and they try and do the same thing again. I wonder, as you mentioned, how would it look like if you actually had maybe a fixed restart module on a learning agent? I think that would be like a really interesting future direction.
Yeah, so on learning agents, it's a bit difficult because the AI Birds framework actually only provides you the base game and basically the action robot, which allows you to interact with the game. It's a bit hard to gather data because Angry Birds runs in real time. And we don't really have, well, we do have means of simulating it because Angry Birds is built in box 2D. But it will probably be a good idea to build that into when it's training. That's actually something I'll be working on right now.
Nice.
So I'll be working on the Eagle's Wings agent. So the Eagle's Wings agent uses 5 heuristics, and it uses a trained model to determine which heuristic to use on a certain level. So for the past few months, I've been working on adding the restart as another heuristic on top of this model and seeing how well it works. It actually does improve a little bit.
Thank you.
Any more questions? Okay.
On some of your recent benchmarks,
on some of your graphs, the agents with restarts, they don't have any score. Could you please explain a little bit why it means like they haven't hit anything, or?
So basically, the data agent, it's chosen to use a specific heuristic for this level, and it's a very high score for this heuristic. So we told it to restart, and it's taken into account that the level's being reset, but it still decides to use this heuristic because the score for that heuristic is so high. So it's trying to do the same thing over and over again, and we're just having it restart over and over again. So it ends up never solving the level. And it solved the other one because after 8 minutes we gave it a timeout, so if it didn't solve it, just move on. Okay.
And the second question is, you mentioned 5% whoop-in performance gain, but how much do you need to beat humans in the competition?
How much does that look like? It's about 35%. Okay. So another reason why, like I say, we probably need something radical because these agents are not really improving that much, right? Year on year, they're getting like 2, maybe, not even that usually, performance increase. So I think these restart heuristics does help.
May I have a very quick question related to that? Is it true that most agents don't ever consider the possibility of running several birds simultaneously, like people do? You shoot the first bird, and while it's flying, you shoot already the second bird.
So the Angry Birds framework
actually
has a sort of timer between shots. Only recently has it been introduced the fast shoot, which basically just shoots the birds. Like the agent gives a order to shoot the birds, and it just flies them really quickly.
Yeah.
But
well, the thing is, suppose you have, I don't even care about birds simultaneously, but suppose the physicist is still working on some falling blocks, and at the same time it's not yet stable, they're still falling, but you already shooting the second bird. So do the agents use that?
some agents have been using the fast shoot, I believe.
Okay. So I mean, but is it crucial for achieving, like you said, something radical? Do people use that?
Yeah, they do, and it doesn't really change too much.
Okay.
But they have the same strategy, and they should just do it faster. It's still the same strategy. They're not gonna.
So basically, we don't know why people are so much better.
Yeah, I guess.
Okay.
But
Okay. Well, I think it's time to finish this. Let's take the review. The review is still boxing. Okay. So then let's move on to the next talk. Describing game AI using highlight cues for generation of playing gameplay. It's going to be Ruck. Thawonmas? Okay, great. So please. You have 1 minute to prepare.
Hi, good afternoon, everybody. So this work will be presented by mainly by my student, Ryota, Ishii, and me from the Peng University from Intelligent Computer Entertainment Laboratory. And okay, there is no time in introducing my laboratory, but okay, so far around 50 of my lab graduates have joined some Japanese company. As you can see, hope you know some of them there. And we are a relatively large-scale laboratory, around 40 students. So this one, the introduction of this work. This work is about using AI technology, applying AI technologies to online streaming. Why? Because nowadays the population of people watching gameplays rapidly increasing. So it's a really real business. The number of people watching gameplay is said to be higher than the number of people watching movies online. And in 2017, my colleague and I proposed this concept called procedural play generation, trying to come up with a nice AI to continue generating nice gameplay, live streaming gameplay. At that workshop, Japan AI, same year workshop on what's it next for AI in games, which are organized by 4 organizers. One of them is Julian. So that workshop was inspired by that Google AlphaGo incident. So we have to think what to do after AlphaGo came out. And our lab has many answers for that, but we present this as one of our answers. So it's a system, it's like this. So we use AI to generate gameplay, and since there are many people watching live streaming, so we have to come up with a way to recommend only limited gameplay that would satisfy people who are watching your live streaming content. So basically it's a combination of AI and recommender system, in particular group recommender system. But today we will be focused on the AI part for gameplay generation.
After this, we propose a fighting game AI for generating fun gameplay. Our proposed AI uses MCTS and highlight cues, and we show that the gameplay generated by proposed AI is fun. First, I talk about MCTS. MCTS is a popular method for implementing AI. As most of you know, MCTS has 4 steps exists: selection and expansion and simulation and backpropagation. Their steps repeat until the end of the game. In selection, nodes are selected from the root node until a leaf node is reached according to upper confidence bounds 1. It is called UCB1. In expansion, child nodes are created if the number of digits is higher than a threshold and the depth of the tree is lower than another threshold. In simulation, all the actions in the selected path are executed. At the end of each simulation, the evaluation value of each node in the path is calculated. In backpropagation, the evaluation value obtained in the simulation step is backpropagated from the leaf node to the root node. After backpropagation, the next action is then chosen among all of the direct child node of the root node according to a given recommendation policy. In our case, we select the child node that has the maximum evaluation value. Next, I talk about highlight generation. With a repeat in sports broadcasting, it's necessary to generate highlights that allow audience to see exciting scenes at their convenient timing. However, the manual generation of highlights is time-consuming. So, many automatic methods for generate highlights have been proposed. In this paper, we focus on 2 highlight generation methods. In boxing, the method uses 2 cues to generate highlights. camera flash Q camera flash Q evaluates the reporter's camera flash. If the camera flash exists in the scene, the Q gives a high evaluation value. Next, distance Q evaluates the distance between the players. If the distance is close, the Q gives a high evaluation value. Next, in basketball, the method uses 5 Qs to generate highlights. Audio Q evaluates the volume, the volume of the audience cheers and commentator's voice volume. If the volume is large, the Q gives a high evaluation value. Next, score differential Q evaluates the elapsed time of the game and the difference between the two teams' score. For example, in this situation, this period is just before the end, and the home team score is higher than guest team's score. And after 1 second after, the guest team succeeds 3-point shoot. So the guest team score is higher than home team's score. In this situation, the Q gives a high evaluation value. It is because people tend to be more excited when the two teams' score becomes close or reversal near the end of the game. Next, player ranking Q evaluates the player rank in the team based on points per game. Points per game is calculated from previous game's results. If the number 1 player gets point, the Q gives a high evaluation value. Next, basket type Q evaluates the shoot type. For example, dunk shoot is a high evaluation value, but normal 2-point shoot is a low evaluation value. It is because people tend to be more excited when the player used a cool shoot. So if the player used cool shoot like a dunk shoot, the Q gives a high evaluation value. Next, motion Q evaluates the player's movement. If the players moved actively, this Q gives a high evaluation value. In this research, we select and modify certain Qs from these 2 previous works for our work. Next, I describe our proposed method for generating gameplay to entertain spectators. Our hypothesis is that a fight between 2 AI players would be exciting if each AI selects their action based on highlight cues. In proposed method, we introduce 3 highlight cues: score transition, and action, and distance in the evaluation function of MCTS. Score transition gives a high evaluation value if the player used a high damage action as the time is closer to the end of the round. We expect that this cue should make a big reversal occur near the end of the round. Next, action cue gives a high evaluation value if the player used a high visual effect action. Rank actor is there. For example, special skill, it is named strong Hadouken, and strong upper, this is named Shoryuken. If we expect that This queue should make a fight visually enjoyable. Next, distance queue gives a high evaluation value if the player was fighting closer to the center of the screen. Fight actively. Yeah. We expect that this queue should make the close fight occur at the center of the screen. Next, I describe the experiments and results. In experiments, we used fighting ice for a game AI competition and for research. And we use 5 AIs. AI 1 to 4 used the proposed method. Each AI used this set of weights. MAI is sample MCTS AI of fighting ice. We compared their results. In our research, we carried out 2 experiments. In gameplay analysis, we generated 1,000 rounds of gameplay for each AI and analyzed them under 3 criteria. In user study, subjects watched 2 gameplay video clips generated by one of AI 1 to 4 and MAI, respectively, and evaluate which gameplay is more fun. We compared the number of votes in each comparison. First, I described the result of every HPD. In AI 1 and AI 1 and 3 and 4 results, high variances occur near the end of the round. These AIs use score transition queue, so we can say the queue is effective. Next, I describe the result of AURA. AI 1 and 2 and 4 used the action queue, but this queue is not effective for rank 1 action, special skill, but contribute to rank 2 action and rank 3 action. Next, I describe the result of ADBTC. In AI 1 and 2 and 3 results, the players battle in close range. This AI uses the distance queue, so we can say the queue is effective. Next, I describe the result of the user study. In first user study, many subjects say AI 1's gameplay is more fun than MAI's gameplay. But in the rest, second study and third study and fourth study, the trend cannot be seen. So we can say AI 1's gameplay is more fun than other AI's gameplay. Next, here I want your cooperation in participating this quiz. Please watch 2 gameplay video clips and evaluate which gameplay is more fun. Let's start. This game video clips is 30 seconds. Sorry. Okay. Next movie. Watch, please. Okay. Okay, finished. I asked about which gameplay is interesting. Please raise your hand. First gameplay is interesting. Thank you. Second gameplay is interesting. Okay. Thank you.
Okay, so I conclude here with this slide, so questions are welcome. Yes.
Oh, questions. Sorry.
Questions. Yes.
Thank you for presentation. My question is, have you considered current industrial examples of your work? Because the only thing that I can remember in Overwatch game able to automatically show some kind of interest moments in the end of the same match.
You mean a kind of highlight? Yeah, we know that some games have highlight mechanics, but since they don't actually reveal how they do that. So if you know, we are not able to find documents that say how they do that. So if you know, please let tell us. Yes.
I can share.
Yes.
Because
Yes.
I got such.
Okay.
More questions?
So, was that the answer you expected to the question or the other?
Yeah, you gave us the right answer. That's why I hugged him.
More questions? We still have a bit of time.
So one for me. So these evaluations are handcrafted evaluations. Have you thought, at least imagine perhaps maybe not for Fighting Ice because there isn't an international competitive scene, but have you thought of other ways in which you could perhaps extract evaluation functions from maybe professional players that are maybe very that may feature very interesting gameplay? So have you thought about using data mining or some sort of data science approach towards computing these evaluation functions?
Yes. As far as this competition platform is concerned, we don't have that much data yet. But we plan to do this, just like Angry Birds AI competition, to have some AIs play with real human players next year from the next competition. And then we hope we could get some useful data for data mining research, as you mentioned. Thank you.
Okay, then let's finish that, and thanks again to the presenters. Well, and then the next talk is entitled Ensemble Decision Systems for General Video Game Playing, presented by Damien. Okay, Damien.
Yeah, sure. Should I do that just now? Yeah. There we go. All right, sit down. Okay, I'm Damien Anderson, and I'm here to talk about ensemble decision systems for general video game playing, and the extremely exciting results that we got while exploring this idea. Now that your expectations have been managed, we shall carry on with the rest of the talk. So, oh good, it's not come up here. Oh well, I'll just have to look up here. So basically, as we're going through this is the structure that we're going to follow. We're going to talk about the problem first, then the actual ensemble decision systems. What are they, and why are they cool? The experiment that was done to evaluate them, the results and discussion, which is going to be kind of one-sided, to be totally honest, and the conclusions and future work we're going to carry out, followed by an obligatory any questions slide. So first of all, we'll focus on the problem itself. So, general video game playing. How can we develop an AI agent that can play any video game on Earth, basically? That's one of the main questions as posed by the general video game AI framework and competition. And basically what the GVG AI is, if you aren't aware already, is a It's a simple framework that allows us to quickly create games in a text-like format. And it's also, what's really interesting about it is that the game that your AI is going to play is unknown to both the designer and the agent itself. So there's a real restriction on the amount of domain knowledge that you can incorporate into your agent. You have to apply general strategies in order to get something that's effective. There are a few limitations on what you can do and how much time you have to think about the problem. So first of all, you only have 40 milliseconds in which to return an action to the framework. And secondly, it's single-threaded. You can't use any concurrency whatsoever. So it's not an awful lot of time to think about what you want to do in a certain situation. I can't think that fast. So there's been a lot of progress in this particular area. There's been great answers to this with Monte Carlo research, Rolling Horizon, Open Loop Spectrumax. We've had a lot of interesting things, but there are a class of games that are particularly difficult for any algorithm, in fact, to solve, which are deceptive games. Now, these games, I will admit this is not my artwork. This is my girlfriend. She's much better at this than I am. You will be exposed to my artwork later. I'm sorry. But basically, there are different situations that designers and competition organisers can implant into a competition in order to try and deceive things. So we already had a little bit of an example of that yesterday from the micro RTS competition, where they designed a map where you had to create a ranged unit in order to destroy melee units that were stuck behind the wall to finish the level, purposely built to basically deceive scripted or simple agents, basically. In this situation, we've got three ideas here. The first one is a greedy agent. You offer it some reward that takes it away from the goal of the game. Perhaps once it collects the first reward, the door slams shut behind it, and only then it sees far off in the distance the hoard of treasure. The middle example is risk aversion. We can hide good solutions behind bad risks, basically. So that takes advantage of an assumption that many AIs make that good solutions are clustered together. So if we have one single good solution that's surrounded by evil nastiness, then we can typically dissuade the agent from going down there, essentially. And the last little example is stupidity. Essentially, it's generality. It's generalizing the rules of a game incorrectly. So if we learn that jumping is extremely useful for us, right up until the cliff edge, and we haven't learned that that's maybe not the kind of rule we want to be learning about jumping, then we go over the edge and it looks pretty dumb. This is not something that search agents typically run into a problem, because they can evaluate the future with a forward model and see that death is impending. But many learning agents will learn that taking an action leads to a certain reward, and will repeat that even when it seems demonstrably obvious that they shouldn't do so. So there are certain ways around these problems. We can apply something like a portfolio agent, which has a library of different agents at its disposal, and it can then analyze the game and decide, okay, these are the kind of features in the game. We want this agent. This is where my art comes in. I'm terribly sorry. And essentially, this is what it is. A portfolio agent looks at the game that it needs to solve, or the problem it needs to solve, has a library of solutions, and decides this is the one that we want to go for. Now, the problem with this is that it's still open to deceptions. We can analyze this and look at the agents that are comprised within the portfolio and create a game that either has multiple different features that need to be solved, or something that just hasn't accounted for with the current selection of agents. So it doesn't really go beyond what we need it to do. So this is where we move on to a different idea, a new idea. And we had this idea to bring together a team of extraordinary algorithms. Some of you may see where this is going already. Yeah, there we go. And bring them into an ensemble to get them to work together to analyze states as one single unit, rather than having one algorithm for one game, basically. So in contrast to Portfolio, where what we're essentially doing is selecting an agent for a game, in some ways what we're doing here is selecting an agent for each time step, in a way. Or there's different ways of doing it. But essentially, unfortunately, I couldn't call it the Ensemblers. I tried, but it doesn't really work. So this is what a very basic view of what an ensemble decision system could look like. It's made up of 3 components. Voices, which are essentially the algorithms that we want to incorporate into the system. The arbiter, which makes the final decision on what we're going to do in a given state. And opinions, which are what the voices return back to the arbiter. And opinions are basically the desired action that the algorithm would like to do, along with a confidence value to say how confident it is that that's the right action. So it works sort of like this. A state comes into the system. The arbiter passes that state to each of the voices. The voices then carry out their own individual analysis and return their opinion to the arbiter. And then using some sort of action selection policy, it then makes its final action, and that's what's actually carried out by the overall system. Now, I've temporarily forgot what's next. There we go. So there's obviously quite a number of ways that we can customize this. We can select a whole myriad of different algorithms to be a voice. We can change how the opinions are returned. We can change how the arbiter selects which action is the best one to go for. And the ones that we have tried so far are what's up here. So for action selection policies, we tried a democratic process where essentially each voice's opinion is actually a vote, and whatever one is most desired and democratically elected by the populace of voices is what we carry out. There's the highest value, which is essentially whichever action has the highest confidence is what we're going to use. And random, which is random. For the algorithms, what we essentially did is a number of sample algorithms that are provided as part of the GVGI framework, and we took a number of them and converted them into this system. So all that essentially involves is, instead of getting the algorithm return an action, it returns an opinion. So action plus confidence value instead of just action. There are no other changes to the actual internal operations of any of the sample algorithms from the GVG AI. And the ones that we've taken for this was Monte Carlo tree search, rolling horizon, random search, and open loop expectomax, which, just to keep that short, I'm going to call it OLETs for now. And then the last little thing that we tried as a bit of variation was to try different arbiters. And that's basically different ways of processing this. So as I mentioned earlier, we have 40 milliseconds to make our decisions. So a single algorithm can use the entirety of that. But if we are going to use multiple ones in a single threaded environment where concurrency is not allowed, then we need to split that time up. So we tried 2 different ways of doing that. The first is, if we have 2 voices, we split it in half. Or if we have 3, we split it in a third. So 20 milliseconds or whatever. The asynchronous one is essentially what we do here instead is, if we have 2 voices, for example, we will make our decision after 80 milliseconds. So we'll allow each algorithm to do the full 40 milliseconds of decision time, but then post a nil action to do nothing, and then give the next voice its full amount of analysis time, and only then after each voice has had a full 40 milliseconds do we actually make the action. And that was to try and see if that would have any difference on performance. So what we also did is we combined this with some previous work done by my fabulous colleague over there, which can be found here. And what we did is we combined this with a number of different heuristics for evaluating different goals within games. So we have the maximize exploration, which maximizes exploration of the game world. We have maximize winning, which tries to look for the win condition of the game. And then we have knowledge discovery and knowledge estimation. Knowledge discovery is essentially discovering what happens when I interact with something in the world. So if I punch this, does it punch back, or does it fall unconscious, essentially? Knowledge estimation is essentially we try to predict what will happen for the interactions without actually experiencing it. So what will happen if I punch, something, essentially. I don't know why I like punching, maybe because of the Avengers reference from before. And what we essentially did was we combined these heuristics with the voices and just basically analyze what happened in those situations. So next we'll get on to the actual experimental setup. So these are all of the agents that we developed for this. The full details of the ensemble agents in the 6 are in the paper. But all of the sample agents there on the right are basically just the sample agents provided by the GVGI framework. You can get a little bit of an idea what some of these are doing. The bottom two ensemble agents are obviously based off of the OLEX algorithm with slightly different heuristics, and one is asynchronous while the other one isn't. The MCTS is using MCTS. The other three are basically using some of the findings from the previous work, which was they had run the experiments on with different heuristics to find out which algorithms worked best when paired with a certain heuristic. So in this case, we're basically using the best algorithm for the heuristics that we're using in that particular case. So we then picked a whole bunch of games from the GVG AI. I will not describe any of them. There's quite a lot, but essentially what we did was we ran all 5 levels of each game. We ran each level 30 times for a total of 150 runs per game for each agent, which then generated 4,200 runs for every single agent. Oops, there we go. And now we'll go on to some of the results there. So first of all, there's 2 ways of classifying the results here. There's the fact that it wins the games or not, and there's the how many games can the agent actually win, what we call the generality of the agent, which is one of the real goals of the GVG AI. How general is the agent? And first of all, what we can see here in first position is the sample OLEX agent. It's got, it uses the formula, the F1 point scoring system, which I meant to mention earlier, but I forgot, so I'll do it now. The GVG AI competition uses that ranking system as a way of creating its results at the end of the iteration of the competition. So we've ranked it by that here in order to be true to the competition, but we've also shown the win rate of each agent, as well as how many different games was it able to complete. And that's essentially, was it able to get at least one win in every unique game? So what we can see here is we have the sample OLEX in first place based on the formula, the F1 ranking, and its win rate. But we have the ensemble agent, which is one rank below, but is able to complete 2 entirely different games compared to what the original algorithm could do. So we, with only a drop of 2.1% in the overall win rate, basically. So what we've done here, we've taken a small drop in overall win rate across the 28 games, but we've actually managed to solve 2 completely different problems that the base algorithm is not capable of solving. And that is a similar pattern that we see throughout the ensemble systems compared to their base algorithms. So you can obviously notice there that the 2nd, 3rd, and 4th positions are all ensembles. And we can also see in the sample MCTS algorithm is in 5th position with 40% win rate and 19 games won, whereas the direct comparison ensemble, the MCTS EXP-SC, which is in the 10th position, has taken a 6.71% drop in win rate, but is able to win 3 entirely different games on top of the games that it could already win for being MCTS. And these are quite encouraging results. This here is a heat map of the win rates for every single individual game across all of the agents. And it's ordered by the overall win rate for the entire game. The darker the square, the higher the win rate, essentially. So some games are very easy and some are much harder. But there's a few little bits I want to point out to everybody. So first of all, this is Lemmings. Lemmings is a deceptive game because in order to win the game, you have to spend score. So essentially, it works exactly like the game Lemmings. You have to basically mine a path through so that the lemmings can pass through safely. But every square that you mine costs you score in order to do that. So the score doesn't lead you towards the win. In fact, it takes you away from the win if we're trying to just maximize score. However, we find that the ensemble agents are able to achieve some success on this game compared to all the sample agents, which are not able to win it whatsoever. And in particular, the OLEX ensemble agent gets pretty good results on the asynchronous and the synchronous arbiters. And on the right here we have a spider graph, which is basically showing this sort of anti-correlation, or sort of rather correlation of score versus win rate, basically. So the next little thing I want to point out is Sister Saviour. Now we don't have the score for this because Sister Saviour is another deceptive game where if you win, you've basically not been tricked by the deception. A win is classed as not being fooled, essentially. And in this game, we've actually achieved almost 40% win rate on Sister Saviour with the ensemble agent. And this is again on a game that the base agents cannot win whatsoever. The next example are sort of negative examples for our ensemble. And these are Plaque Attack and Avoid George. Now, what we've seen here is we're still able to win the games, but we've obviously taken a win rate loss in order to get that. Now, part of the reason for that is, particularly in Plaque Attack, is because Plaque Attack is a particularly large level. And as soon as we put in an exploration heuristic that loved exploring, that's what it did. It explored a lot. So the problem there, though, is that there's sort of an internal hidden timer that goes in the game, that if you don't complete the objective before the missiles destroy the bases, then you lose. However, if you have a large map, the exploration heuristic goes on a large trip, buys a shirt, and then comes home eventually. So, but we're still able to win those games even if the win rate has been affected significantly. So then we have our Pac-Man graph, which I did not plan in the slightest. That's just the results. I'm so happy. And this is basically looking at one of the easier games where the performance isn't actually as clear to analyze because all of the agents tend to win. And this is for Invest. Invest is another deceptive game, but the idea is that winning is exceptionally easy, but scoring well is extremely hard. So we can see here, the blue dots reference the win rate of each agent, whereas the green dots refer to the score that they're able to achieve in each, or for each agent, essentially. So we can see that the Ensemble's best four, Diplo, and MCTS SC are able to score great scores while keeping their win rate high. And all of the sample agents, once again, are getting very low scores. The OLEX SC gets slightly higher, which is a good sign that it's at least managing not to be completely deceived by the game itself. It's finding some solutions, though it's obviously not as good as some of the other ensembles that are there, basically. And then our conclusions and future work. So, we sort of concluded that the Ensemble Decision Systems, or EDS, improves the generality of general video game playing agents. And our sort of conclusion there is that that's a much better starting point for improving performance, even if we're taking a slight win rate loss compared to a single algorithm, because we're able to solve 27 games instead of 25. Improving that performance should, in theory, in the future, lead to a more general, more powerful agent. And also, yes, it becomes a very viable option for GBGP, especially when we remove the restriction on concurrency, because each voice can be run in parallel, and it's not quite so straightforward to think about how do we parallelize something like Rolling Horizon or Monte Carlo and so on. It's not quite as clean cut, whereas this is immediate. We can just, or for example, if we want to add an additional behavior to an ensemble, we just design a purpose-built voice that does it, put it in, and it becomes part of the decision-making process without any adaptation or significant changes to any of the other voices, essentially. Future work, we want to do a comparison with portfolio agents, because those are the highest performing agents currently in the GBG AI. I've begun that work at the moment, and so far we're looking really good. We're getting more general results, although the win rate is a bit more dramatically bad. I need to work on that still. We also want to implement an all actions ensemble where every voice is required to return an opinion on all actions. So there's a strange and interesting possibility of selecting an action that none of the agents selected as their first action, but possibly the second best option, which from multiple points of views is still an acceptable point of view to go. Further experiments, because we'd like to take some machine learning voices and plug that in with search algorithms to see what happens there. Experiment more with the concurrent ensemble, which is currently undergoing, and build a more sophisticated arbiter, which can maybe have purpose-built voices that decides for certain situations, like a survival one that picks up negative states or lost states. And the last thing, which I've put in entirely because Matthew has hounded me for the entire conference, is to create a Ludi version of this, because Ludi is great. Put the weapon down, Matthew. Thank you very much for listening, and any questions?
So let's have one question, maybe. Who really wants to ask?
Thank you for your talk and very nice presentation.
Yeah.
But you have some random behavior agents?
Hello? You have some random behavior agents or some random decision systems inside your ensemble. Which confidence score do they have, or which confidence value do they have for a random decision?
The confidence values are determined by the voice itself. Mm-hmm. So we're sort of treating the voices as experts in a given situation, if you think of it like that. Now, with the random one, that's a little bit harder. What we do in that case is we essentially take the score that it feels like it's earned throughout its randomness, and then apply that as a confidence value, because there's no real way of interpreting that in a sensible way, to be honest. So we just sort of say, okay, how much score did you think you would earn in that situation, and that will do. Okay. It's not the best way, but I don't know of a better way to really do it, to be honest.
Say, I know what to do?
Yeah. Exactly. But yeah, that's it. I don't have a great answer to that, I'm afraid.
Okay, great. Thank you.
Thanks.
Well, thank you very much. Yeah, going on to shorter talks, so will be 15 minutes. So the next talk is macro and micro reinforcement learning for playing 9-ball pool, right? Presented by Chen and Yujun Li. Okay, Chen.
Do I have a pointer?
Yeah, maybe. Do you have pointers?
Oh, no. I don't need.
Okay, fine. After people, okay. You can put it in. Okay, thank you.
Good afternoon. Today I'm going to share with you an application of reinforcement learning for playing the 9-ball pool games. So what are we working on? We want to train an AI robot to play the pool games, but we don't have a real robot or robotic arms. So we train the AI in a simulation environment. What we care about is how AI make decisions, specifically as shown in each sub-figures above. Our AI can get the state information from the simulator and send back action, telling the simulator what speed do you want to shoot or what angular on the table. There are other action parameters, and I will introduce later. Next, I will briefly introduce the pool game rules. I'm not an expert in pool games. If I'm wrong, please correct me. Pool is a classification of cue sports. Cue sports is the sports that use the cue stick to play. This is the cue stick. It is played on the table with 6 pockets, 1, 2, 3, 4, 5, 6. In general, the objective of the pool game is to deposit the object balls. These are the object balls into these pockets with the help of the cue stick and the cue ball. There are many variants of pool games. For example, this is the 8-ball games. This is the 9-ball. This is snooker. British people like playing snooker. I know. It is generally accepted that 8-ball is very easy. Most beginners start playing pool games with 8-ball, but 9-ball and snooker are much more difficult to master. We choose the. Sorry. Oh, sorry. It doesn't work. We choose 9-ball to train our AI. 9-ball is similar to other variants, but the key point is in 9-ball, the player is supposed to deposit the ball in a fixed order, in an increasing order, from the first one to the last one. The player who successfully deposited the last ball wins the game. That is, the previous balls from 1 to 8 does not score. This is different than at snooker or 8-ball. For example, if the player successfully deposited the third ball, the ball 3. The only choice of his next objective is ball 4. If he fails to deposit ball 4, his opponent will continue. Next, I will introduce the environment. Like other IR studies, we need a simulated environment. The pool simulator is based on these two articles. Will and Michael proposed a novel way to simulate the pool ball motions, and the proposed method is significantly faster than frame-by-frame calculation. For example, if you use a physical engine like Bullet or Mozgovoy to run frame-by-frame simulation, it is very ineffective. The proposed our environment is a modified copy of this implementation. We add some new features, including adding IL APIs and enable utils functions such as dump and load in environment. That is, this enables us to do MCTS because we can go back to any time point of the game and load the state and continue to play. Here's the demo usage of the environment. It is very simple to use, almost as same as the OpenAI gym. For example, you can use get state to get the state from the simulator. It is an NP array of size 10 by 3. For each ball, we use a 3-dimensional vector to represent its position. The first two coordinates indicate the position on the table, and the third coordinate indicates whether it is still on the table or it has been already deposited. One can specify the GIF file name in the ACT API, then you can get a GIF replay. This is the GIF replay. Now it is open source on GitHub, and it is still working in progress. What is the action of Neighbor Pool AI? Pool is a complex game, but the action for AI is surprisingly simple. A 5-dimensional real vector is enough. There are two groups of parameters. The first group describes how the Q stick moves. For example, we have the speed v of the Q stick, and we have a percent. It is the angular on the horizontal plane. It takes value from 0 to 360. Another parameter is phi, because you can lift your stick up to hit the cue ball. So the phi takes value from 0 to 19 degrees. When the cue stick hits the cue ball, the point of contact can be off-center. Hitting the ball off-center will cause the ball spinning, and spinning is important skills in pool games. For example, like this. Keeping the ball off-center will cause the cue ball spinning. The reward function is very simple. If the last ball is deposited, the reward is 1. If other balls are deposited, the reward is 0. If fails to deposit any ball, the reward is -1. So what's new? For reinforcement learning, pool game is a new kind of game. In some ways, pool game can be viewed as I don't know why. Presenter view. So what's new? Pool games is a continuous version of Go and chess because each action has a long-term effect. So player needs to do planning when he playing pool games. Another feature of pool games is that it is very hard to predict the next state because after a shoot, the position of all balls are quite random. So it may be a difficulty for reinforcement learning robot. neighbor pool need planning. Which of the situation is better? Maybe no one wants to face the situation on the left. So experienced player can control the position of the cue ball. For example, in this GF, he controlled the cue ball to move closer to the next object ball in order to win the game. However, there are some talented players can easily deal with those difficult situations. But planning is also very, very, very important for most players. So what can AI players need? AI player need a value function to estimate how good the state is and need a policy function to generate actions. But simply applying this reinforcement learning algorithm like PPO does not work. The reason is that it is very hard to get positive reward. So we have a new method. We propose a hierarchical action approach. The intuition is that there are lots of target pockets to choose from. For example, one can deposit the yellow ball to this pocket or this pocket, and there are many different ways. Choosing a different path will affect the next state of the next time step. We use a macro and micro approach and use MCTS to explore. I will explain. A macro action is to choose a pocket to deposit the object ball, and a micro action is used to generate the speed or the spinning position or do this minor change. And we use MCTS to explore. I will explain in this video. Here is the demo video illustrating the algorithms. The first line is the macro action. The robot is comparing the pocket 2 with pocket 4. This block shows the macro action. It generates the speed, the angle, or the left-right spin, or the top-back spin. In the MCTS, the first layer is the macro action, and these are the macro action. We can see first the bot will the bot is trying to compare. Oh, sorry. In MCTS, the bot first chose the pocket as a macro action, and then he do some minor changing. For example, increase the speed by 0.1 miles per hour, or decrease the speed by 0.1 miles per hour. Then in the MCTS search, the next state will be different. We use the next state Q value to evaluate the actions. So we have one trail has one path. The parameters, all functions use a deep neural network as the parameters, and all parameters is updated by a composite loss. The macro loss is similar to the Bellman equation loss, and the macro loss is just the L2 loss. The macro action is updated in a supervised manner. It is learned from the Monte Carlo tree search. Let's continue to the video. From this video, we can see that the AI robot learns to use different speed for different object balls. This is the last ball. here are some statistical figures of our AI. For example, this is the hitting point. The AI likes to use left and right spin. This is the position of the cue ball. These are to-dos. Next, I will try snooker and knowing how to play offensive or how to play defensive. Thank you.
Thank you.
In your system, does the AI have perfect aim, or does it have errors when it tries to shoot?
Random errors, very small errors.
It looked like the AI preferred to use left and right spin and not very much up or
I
down
don't know,
spin.
I don't know the reason why.
Oh, okay.
Does your system learn how to do trick shots? Because the rules are you have to hit the next lowest value ball, but the win is to pot the 9 ball.
Yes.
You can do them in the same shot.
We don't consider this situation.
Okay.
We force the AI to play from.
No. If you say you're aiming for the 1 ball, but you go off the 1 ball and then hit the 9 into the pocket.
These are advanced skills.
Mad skills. Yeah, exactly.
What about jumping over?
It seems it is not allowed. It is illegal. I don't know. I'm not an expert.
In pool?
Okay. But we have a parameter that lift the cue stick. It can generate the jump of balls.
Okay, any more questions?
And what is the observation space? Are you learning from pixels or?
We use the three coordinates to represent a ball. There are 10 balls in total, so 30 dimensional real vector is the space.
Okay, well, thank you very much. Let's thank our presenters. And it's time to move on to the final talk of today's session. It's entitled Create an Effective Fighting Game AI System with Gamygdala, presented by Kaori. Name and dates.
Oh, no. Should be.
Should be. Okay.
Should be.
Should be. So did it actually work, this adapter?
Well, maybe here.
It looks like it should be.
Should be working, but it doesn't. Okay, yeah. Sorry for the delays. In a demo session where tutorial session where we had no laptop, and then we couldn't make the projector running, and then the tutorial gave up and said, okay, I'm going to use just whiteboard and markers, and the room had no markers.
That's so weird.
We are still not that desperate.
Should be a tutorial.
Yes, exactly. It was how to do that. Yeah.
It's getting weird.
My own PC.
Oh, maybe.
What about BGMI? What do you think about it?
Does it work now? No, it works.
Oh, yeah. Okay.
So it's gonna be. Where is it? This one.
I think so.
You better know. This one.
Okay, cool.
Okay, good. Yeah.
Okay. Okay. Hello. I'm Kaori Yuda, and I'm going to talk about creating an effective fighting game AI system with Gamygdala. For one-to-one fighting game, non-player characters operated by AI is already good enough to defeat human players. So we move on to make enjoyment, and we decide to make the NPC human-like behaviors. And we made it by Gamygdala, which is the emotional appraisal engine, and universal fighting engine. This is universal fighting engine look like. It is an open source framework, and we can make a demo on Unity like this. UFE includes fuzzy AI. Fuzzy AI evaluates the information of the scene and calculates the desirability of each given action, and translating the AI decision directly into user input. And the good thing of fuzzy AI is we can modify it in real time. Fuzzy AI got several selected options, and this is 3 of it. And behavior style, we can choose from very defensive, balance, very aggressive, and aggressive. Time between decision, we can make we can decide a minimum time to make a decisions. Rule compliance, we can make it to choose like more systematic or more random. And this is our main topic, Gamygdala. Gamygdala is an emotional price engine, and it automatically generates some emotions by setting goals and briefs. Goal is the name state which character wants to achieve, and the brief is annotated events that move the characters towards or away their goals. This is the goals we made. Win by KO, achieved when the opponent's house level reaches 0. Win by points, achieved when the round is over and the house level is higher than the opponent's house level. Keep high moral, we made it because just win by KO and win by points is not really, it's too simple and not really exciting. So maybe I can explain it to the next slides better. We made it to almost opposite goals, lose by KO, lose by points, and keep low moral. And this is examples of brief of UFE agent. When NPC hits the opponents and reducing its health level, the brief of cause damage will occur. The goal of win by KO and win by points increase that time, and the lose by points will decrease. Spend time winning occurs every second as long as an NPC's health level is higher than the opponent's health level. The goals of win by points increase and lose by points decrease. About to win by KO, which occurs when the opponent's health is very low. the goal of high moral increase and the goal of low moral decrease. And the mere 3 successful attacks, it's also like about moral, and we have quite a lot of waves like this. Here is the results. So in this game, NPC never attack to the opponent and lose by just like a human attack to NPC and lose. And the blue line is the anger, which occurs, the undesirable event is occurs because the like such as because the so it is losing and such as lose by KO or lose by points is like about to the event of lose by KO or lose by points will occur. And red one is fear. It is occurred by the undesirable likelihood for a goal increase. And resentment is the yellow one. This is the desirable event for opponents. So for human player, and also they feel fear conform and same level. Fear conform and distress in same level, and which is moved by the goal. So goal is about to reach or reach it. So it's quite low level, but yes. Here is the opposite situation. NPC wins without having any damages. So in this game, hope is really high, the blue on top. So it is because of it increased by the likelihood or desirable goal. And the yellow one is gloating, which is because in this situation it is not desirable for human players. Certification and joy is about the same level, and it is also rated for goals achieved or almost achieved. Okay. So it is almost similar to the previous one, this one, but for this one, NPC attack human player, anti-human player's health point will be half, so it stopped attacking around 55, and you can see the after 55 it's slowly increasing. It is still increasing because we have the winning by points, goals, and losing by points or something like that. For this one, NPCs and opponents attacked each other for about the same level, but NPC wins at the end. The orange one on top is red one. On top is hope, and the hope and the glowing yellow one is same level at first, but at the end hope grows because of I think high moral, and resentment and fear is same level as blue at first and gray for the end, resentment. And resentment also goes up at the end because of high moral. And we have fears and angers. Based on psychology theory, we made a rule of how these emotions should translate into actions. As I told, there are several options for fuzzy AI, but let me just explain about behavior style because there are so much things. When they feel hope, joy, satisfaction, they're supposed to act balanced. And when they feel anger, they're supposed to act aggressive. And when they feel disappointment, distress, or fear, then they're supposed to act defensive. In this work, we made emotional character by not building AI from beginning but combined. It shows that we can connect Gamygdala to Unity-based game. So it means we can connect to other, like more players or more enemies game, and which might be more complicated and more interesting. For this work, we didn't translate it. We made it translating emotion by the psychology basis, but we didn't make the test to like actually how they move, like based on how they on the game. So for our future game, we will test if it's gonna be really human-like or not, or like if the human players feel really interesting or unique of it. Thank you very much.
Emotions, you mean the NPC emotions?
Yes.
So it might also be interesting to consider the human player's emotion.
Actually.
And based on that, so the NPC should do some actions that according to the human player's emotion.
Yes. Actually, for this graph, on the paper, we just added emotions to NPC, but we also added to the humans. So, like, if we didn't add it to the humans, then NPC never feel gloating or resentment. But we actually put it onto the human players. So it's not the real emotions, but we expect how they're supposed to feel.
Yeah, so what do you mean? Do you mean emotions by modeling emotions, or by attaching some sensors to humans and, I don't know.
Yeah, facial expression.
Like that.
Like that.
Okay.
Expression.
So if the human player is angry, what should NPC?
Like take a picture of a human, take a camera, and by looking at my face, you can try to guess what I feel.